Okay, so you want to blink an LED, but not the easy way? Get along with this video and you will know how. We will divide this code in three parts. First is the device specific header file. In this case, I was using STM32 blue pill. So this is the device specific header file. Then I was working on the GPIO ports. So whatever different configurations in the GPIO, what we can configure, handlers and clock controls, different input output operations, what we are doing, we will define this in GPIO header file. And how will this basically different functions work will be defined in the driver.c file, basically referring to the reference manual and configuring it respectively. And at the last, we will basically call this header file in our code and like call those driver functions directly. What happened in the header file is basically I referred to the reference manual, and in that reference manual there is a section called as memory map providing me all the base addresses. So like if I go into the data sheet and look for the block diagram, so I know that the GPIO port A lies on the APB2 bus for my specific microcontroller. So it was necessary for me to basically define whatever different peripherals which were present on the APB2 peripheral, which are here. So yeah, the most important means peripherals used, their base addresses are defined here, and then there is a structure which is made here defining all the register, because no matter which port we are using, whether it is port A, B, C, I mean so on to G, the registers will be same. Only the difference is their offset means their base addresses will be different, which is then passed using these macros like the GPIO A, the port A base address is passed to this structure, and the offset value is basically 0 cross 0 for this, then 0 cross 4, it gets increment by 4. So yeah, the offset values of these registers is fixed, just the difference is the base address of these registers is different, which is defined using these macros. And then to configure the clock, we need RCC registers. So here is the RCC register complete structure, and then a macro is made passing the base address of that RCC register so that they get the proper offset values. And another for means a short way to enable or disable clock. Like instead of doing manually inside the code, I can just call this function, which will basically enable the clock for A, B, C. Same for I2C, same for SPY, same for USART, and yeah, same for the disable part. And this simple thing might able to make the code more readable. So these macro definitions are being done by referring to the reference manual. Like suppose if I want to enable the GPIO A peripheral, so I'll go to the datasheet and first look where the GPIO A peripheral lies. It lies on the APB2 bus. So I'll go to the RCC registers, APB2 enable registers, APB2 enable here. So the bit 2 is basically GPIO A. So if I here it is written, if I enable it, the clock for the port A will be enabled, and same for the disable. Like if I want to disable the GPIO port A clock, I will basically reset that bit. And almost everything here is like done using that. Mostly the reference manual comes into play and data sheet for looking which bus does it lies to. But the interesting part was like if we want to basically execute more than one statements in a single macro. So this was the interesting part where we use a do while loop. Like we know that this do, whatever is inside the do gets executed once, and whatever is inside the while keeps on executing. So I'll just pass here 0 such that the while loop never get executed, but I'll make sure that whatever is inside the do statement will get executed. So that's how we can execute more than one statement inside a macro. And this is basically used for the register reset. Basically, if we want to use that same pin again or same port again, we will reset these registers, and for that we will basically again go to the reference manual, and there is this APB2 reset register. So again I'll refer to the bit 2 for GPIO A, means when it goes high it will reset it, but I don't want it to constantly being reset, so I have to make it low again, and that's why I make it 0. Means I first set the bit, like here, I first set the bit and then I reset it, meaning it will clear whatever was inside the port A. So that's why two statements are used. So this was in the all about device header specific file. After completing the device specific header file, since we were working on the GPIO driver, we need to create another header file where we will include the device specific header file. And if you see in the reference manual, the functional description, we can see that the GPIO pin can act as lots of mode. And if we configure the CNF and mode bits properly, we can use those modes in our need. And also we can adjust the speed of the output pin at what frequency we want it to operate. And everything is basically configured in these two registers, port configuration register low and high. Low register is basically from pin 0 to pin 7 and high register is from pin 8 to pin 15. But the configuration is same for both the registers. Basically, for pin 0, we will use these 4 bits, mode and configuration bits. And as you can see here, we can set in the configuration whether the pin is acting as an input or output. And if it is acting as an input, whether we want it as analog, floating, or different type. Also as output, which configuration we want. In mode bit, we will basically decide whether we want to set that pin as input or output. If it is input, then it is fine. But we are setting it as an output, we need to also configure its speed, and that's what is written in this header file, like different speed, different configurations, whatever is needed. The main thing in this header file is the GPIO handler structure. What it contains is basically base address of the pointer and also the configuration part, like this structure. This structure contains the pin number, the pin mode, the configuration mode, and whether does it need up down or not. And this is all basically defined here, like the pin numbers are here, then the pin mode. So what type of mode is, whether input, output, then at what speed, then configuration mode, like whether input as analog, floating, or something else, output as what. So this is basically done in the header file, and these are different functions which we will see in the driver.c file, but these are basically defined here, like the peripheral clock control, which will enable the peripheral clock as we described in the device specific header by enabling or disabling the RCC registers. Important part in this header file is the init function, and as you can see, it takes the GPIO handle as a pointer, and it contains all these informations like the pin number, pin mode, CNF mode, whether does it need up down or not, the base address, everything in order to initialize that pin. And rest are all the different functions, like for deinit we'll just disable the uh, deinitialize, basically reset the register. So for that we only need the base address of that port. And well, these are all briefly written in the .c file. Here we are just declaring it. The main thing we will be using is this toggle output pin because we want the LED to toggle. So that's why we take parameter as that port address and what pin number does that LED is connected to. This will be useful for toggling the pin. Similarly, for so if we want something to write at the output pin, we'll take the port number, the pin number, and what value we want to write. If you want to read, we won't pass any value, right? We just want to read it. And these are quite self-explanatory. The IRQ handling is pending from my side also because this is for handling interrupts and I haven't written the code for interrupts yet. But overall, this is what is inside the GPIO driver. Now, whatever functions we have named inside the driver.h file, we will basically make it work in the driver.c file. So for that, we will include that header file, and once that header file is included, we will write the code for each function. Like here, we are controlling the peripheral clock. So we will take the uh, base address of which port peripheral we want to, means whose clock we want to control, and whether we want to enable it or disable it. So yeah, the code is quite easy because whatever configurations we wanted to do, we have done it in the device header. Like if we want to enable peripheral clock for port A, this is already defined in the device header. So I will just write, if the base address matches the GPIO A, I will enable it. If we want to disable the peripheral clock, I'll again match it and then disable it. So this is quite easy. The thing where it gets quite confusing is this init part, but once you understand it, it's not that complicated because most of the time I have like wrote the code for one if else block and then pasted for the other. So like since there were since there are 4 bits, we will be configuring at one time, like the 2 bits of mode and 2 bits of CNF. Hence you can see here 4 different variables I have made in order to configure them. And as I also told that for pin 0 to 7, this will be the register we will be configuring. For pin 8 to 15, this will be the register we will be configuring. So that's what it is done here. Pin 8 till here and then for CRH. So I think you might now understand whatever code I have wrote for CRL, the same code is used for the CRH. The only difference is the registers, means the name of the registers are changed. And yeah, that's what the init does. Means it checks the mode and then whatever bit we want to set. Like if the mode is a means the if pin is acting as an input mode, so we will go to the reference manual. We want it as an input mode, so we need to reset both the bits of the mode. So that's what is done here. We have resetted both the bits. If it is acting as analog, means we need to give 00 into the configuration bit. So that's what is done here, 00. And yeah, that's the whole point. Means if it is acting an input, we will check for this condition. If the pin is acting as output, we will check for these 3 conditions. This, and then we'll check for these conditions. That is what the whole init does. Once you go through the code, you will understand it. This is the init. Then in dinit, basically we will just reset the values, like which port we want to deinitialize. We will take the base address and just reset it. Well, for reset, I've already told like how we were resetting the this RCC reset register, making it 0 and then 1, which will reset it. So that's what the function call is made here for dinit. So if we want to read from the input port, we will directly read it and return it. Basically, IDR is a 16-bit register. So that's what we are returning here. We can write values, then we can write directly to the output port as well. These are quite easy to learn. And this is the thing which we'll be using for the LED toggle. That is this. We'll be taking the pin number which we want to toggle, and this OR operation is done here, which will basically toggle like 0 to 1, 1 to 0. And yeah, that's what I'm talking. The IRQ configurations are left. Once everything is done, we will write the code now actually to toggle the LED. For that, we will include the GPIO driver header file, and we will also create a fake delay loop, which will basically start from 0 and then go on for a large value, which will kind of create a loop, means kind of create a delay. And since volatile is declared, we don't want the compiler to optimize it and ignore this for loop. So that's why volatile keyword is used. And we made an object of the GPIO handler structure and we access the members of that handler structure like this, like port A, pin number 0. Then I want that pin as an output with a speed of 2 megahertz. Then I want to act it as a push-pull configuration, and since the pin is acting as an output, I don't need any pull up or pull down. So that's what is written here. And since it is for GPIO A, I will enable the peripheral clock for GPIO A and I'll enable it. And I'll basically pass the address of the object to the init function and it will initialize everything. And this is the for while loop which will go on continuously. And here the toggle function is called, which will basically make the LED go from high to low, and the delay function is called, which we have created here. Once everything is done, you can just upload the hex file and then verify it. Once it is done, I have to disconnect the ST-Link and then again connect it. And here's the blinking LED. The blue pill doesn't have a bootloader, so that is why I'm using an ST-Link, which acts as a USB driver to send the code. I hope you have liked this video. If you have any type of doubts, you can ask in the comments. Most probably my next video will be on some protocols where I'll be writing some drivers for different protocols like SPI or UART. And if you want a video on some different topic, you can post it in the comments. I'll try to make one.